Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 35th lecture on the course Maritime Structures, where we are discussing types, construction, pre-service analysis and design aspects offered by Department of Maritime Engineering at IIT Gandhinagar. Hope you have understood the previous components of this part of the course. We are in the stage of now applying these concepts for typical design of tubular members. So we are now looking at the design example of structural design of tubular member. Welcome to lecture 35, where we are going to discuss about a design example under combination of loads. Now, let us say when axial compression and bending, case 1, and axial tension and bending acts together, that is case 1 and case 2 act together, then this will be an indicator of overall behavior. In such cases, we need to do something called unitary check. It's called as UC. For this combined loading, we will try to show you how this unitary check is done by the governing equations given by the code. However, the interesting factor is when you have axial tension combined with hydrostatic pressure, or axial compression with hydrostatic pressure happens, then this will induce local buckling. So, the unit check is related to the local buckling. We will see a design example on this application. I would give a tutorial where you can try this application, but of course, we will discuss the governing equations of all of them in the due course in this lecture. Now, let us take a practical case where a combined action can take place. Let us now consider a typical jacket let us say these are driven into piles, these are the legs of the jacket driven into piles, and this is the ground level. Let us say we know that these legs are braced. So, I am now marking the main legs in a thicker color for our understanding. Now, we can write that these are, of course, there is another leg at the bottom, we are not seeing that. So, this we can mark that as well. Okay. So, these are main legs, and these are braces. Let us now mark the axis of reference for our case. Take for example, a typical member which I am marking here, this member. Let us take this member for design. Let us mark the axis as x axis, then z axis, and then y axis for our reference. Let us look at the brace AB. Okay, we will focus on the discussion, and in the top side there are many, let us say, the building blocks, then the electromechanical equipments, living quarters, helipad, and cranes. All these top sides are going to act on these members, have to be dispersed along the main legs. Okay. Now, considering this figure, for the dead load and the payload which is acting on the deck of the superstructure, main legs will be under axial loads, correct? Where the load has to be dispersed through the main legs. So, the main legs will be under axial loads. Now, the loads coming on the main legs will be transferred to the braces. Because braces are connected to the main legs. In addition, if there are lateral loads acting because of water waves, coming because of wave action, then if the waves are acting along x axis, let us say as we see in the figure, the frame will now laterally deflect. Am I right? Remember friends, these legs are not on the same plane, they are inclined. Therefore, the braces connecting this point and this point will not be on a single plane. Okay? There will be inclination of this because a 3D space frame sort of a thing. So, there is an angle of inclination which is attached to this connection at this point, everywhere you see they will not be on the same plane. Under this system, the whole frame is now under lateral deflection. Therefore, under this condition, based on the cross sectional dimensions, size, shape, etc., there is a chance that the main leg and the braces may undergo buckling because axial compression is acting, can also undergo bending because lateral force are acting. So, therefore, now I can expect a combination of axial compression plus bending acting on the brace. So, now look at this figure, I am taking moment about y, therefore, I can say the braces will be under the combined action of axial compression plus bending My. Now, I reverse the wave direction, look at the same figure, now I apply wave direction along y. So, for wave direction along y, again the members will be subjected to axial compression because there is a load coming from the top of the deck plus bending, but this time the bending is mx, am I right? So, now as I told you, this brace for example or this brace for example will not be on the same plane. Okay? So, now this can result out of plane bending. That is zx and yz or the reference planes and the moments are my and mx. Therefore, the brace AB for example, which is on the different plane because this angle of inclination and this is different. Okay? So, AB is on a different plane now. So, AB is expected to the brace AB is expected to undergo, there is an axial load transfer from the main leg to the brace. So, it will have an axial load. It will also undergo biaxial bending. Friends, why biaxial bending? There are two moments now acting. For the wave direction along x, I get moment about My. for the wave direction along y, I get moment about mx, right. So, there are biaxial bending and axial load. So, it is a worst combination now. So, now based on the effective length of the brace and d by t ratio, the brace may fail in pre-buckling mode. So, one has to check the design for such combination of action. So, friends, it is not only a straightforward application of axial tension, compression, bending, etc. We here see a very complicated situation where there is a biaxial bending possible along with the axial load disbursed from the legs to the braces, right. So, we have to be very careful about using these equations and the notations carefully. Now, let us see case 1. Under compression, axial, okay, axial compression and bending, what happens? Under axial compression and bending, the members should satisfy two equations. Let us say what are they? Fa by Fa plus Cm square root of Fbx square plus Fby square by 1 minus Fa by Fe prime times of Fb should be less than or equal to 1. This is called unitary check. This is called unit check. Let us see what are these values, what are these Fas, Fbs, etc. So, this is equation number 1 which is to be satisfied. The other equation which is satisfied is Fa by 0.6 Fy plus square root of Fbx square plus Fby square divided by Fb should be also less than or equal to 1, second equation. So, both these equations must be satisfied under axial compression biaxial bending. Okay. Now, let us see what are these notations and are we aware about these notations, do we know them? Okay. Let us see that. For example, in the above equation, if Fa by Fa is less than or limited to 0.15, then instead of equation 1 and 2, we can use another equation which is Fa by Fa plus square root of Fbx square plus Fpy square by Fp less than or equal to 1. So, friends, we have got 3 governing equations. Okay. Let us see what are these values in terms of their understanding. In this equation, Fa is the axial stress in compression, we already know that, I am writing them here. Okay. Fa is the permissible or let us say allowable axial compressive stress. We have already seen in the previous lecture how to compute them. Okay. Small fa is actual, we will see that how it is computed. Cm in this equation is called reduction factor. Reduction factor for various cases are different. Let us say this is as per class 3.3.1e. I will give couple of them. For superstructure, legs when they are braced and when they are unbraced. Two conditions. When they are braced, the reduction factor Cm is taken as 0.85. When they are unbraced, again they are taken as 0.85. There are various forms of reduction factor which I will write it here. Reduction factor can be 0.85 on different applications. It can be 0.6 minus 0.4 times of m1 by m2. It can also be 1 minus 0.4 times of Fa by Fe dash or 0.85, whichever is less. So, in this equation friends, we know what is Cm, we know what is Fa, Fb, of course Fy is the yield stress and Fb is the permissible or allowable stress in bending, right. So, we already seen that equation in the previous lecture. So, Fb is known, Fy is known, Fa is known. So, now we can also know now the reduction factor which is useful here. And therefore, I can try to find out this unitary check for a given case if I know the bending stress about two normal axes and the axial compressive stress appearing on this. In case the system is under case 2 for axial tension and bending. Okay. The equation remains same. Whereas Fbx and Fby are computed tensile bending stress. Now, we will take an example and try to solve this and see how we can use this. Now, we will take an example. A jacket brace is subjected to the following loads. Axial load is given, in plane moment is given, out of plane bending is given. Assess this brace for structural fit. That is the question. The data given are as follows. Let us say the data given. The outer diameter of the brace is 762 millimeters. You may wonder how this fraction is coming. Actually, these dimensions are in inches. So, when you convert them to millimeter, you get fraction like this. Thickness, okay, D is 15.88 mm. This is D for our nomenclature. Okay, we know that. Let us say the length of the member, this unbraced length of the member, which is L, taken as 15 meters, small l. Okay, let us take the small l, 15 meters. We take Fy as 345 megapascal. We know it is as same as Newton per mm square. And we take modulus of elasticity as 2 10 power 5 Newton per mm square. Now, for the brace connection in the problem, we take the K factor as 0.9. Okay. Now, in plane bending, you look at this figure which I showed you in the beginning. So, when I apply moment about this, it causes in plane bending. When I apply moment about this, it causes out of plane bending, okay, because this is going to bend out of plane, whereas in this case it bends in plane. So, now I can say for this problem, in plane bending is 800, therefore, I will write down here in plane bending is 800 kilonewton meter. I put My. Out of plane bending is 600 kilonewton meter. Let us check whether this brace is structurally fit. That is a question. So, step number 1. Let us do the geometric properties. Okay. Let us compute the area. You know, for a tubular member, we know the area is given by pi d square by 4. So, now I can substitute this 762 minus 730.24, because 15.88 is the thickness. So, please compute this, friends. I am getting this as 3.72 10 power 4. Let us find out the moment of inertia about the bending axis I, which is pi by 64 d power 4. Okay. So, I substitute them. I get this value as 2.59 10 power 9. Now, I compute something called section modulus, which is Z, which is I by Y max, is it not? I have a circular member, I have the outer diameter, I have the centroidal axis, I am looking for Y max. So, I could now say it is going to be 2.59 10 power 9, that is my I value. Y max, can I say it is d by 2? So, if we substitute that 2.59 10 power 9 by 762 by 2, I get this value as 6.8 10 power 6 mm cube, that is my section modulus. Then I find out radius of gyration, which is square root of I by A, which is going to be square root of 2.59 10 power 9 by 3.72 10 power 4. That is the area, right? Yeah, 10 power 4 square root. I get this value as 263.86 millimeters. Then I check d by t, that is very important for us. So, d by t check, so it is 762 by 15.88, it is 47.98, less than 60, I can use specific set of equations. This is required because the equation changes, we already seen that. Let us do step number 2. In step number 2, we will try to find out under axial compression, column buckling, what is the allowable stress. So, for members whose d by t is less than 60, the allowable compressive stress, please refer to your notes, I am writing the equation, is given as Fa equals 1 minus KL by R the whole square divided by 2 cc square divided by pi by 3 plus 3 KL by R by 8 cc minus KL by R cube by 8 cc cube. This is true for KL by R less than cc, is it not? Let us first compute cc. Let us compute cc our case. Cc in our case going to be 2 pi square E by Fy square root. So, let us compute that. So, square root of 2 pi square into 2 into 10 power 5 divided by Fy we have taken as 345. I get this value as 106.92. You can please check. Let us also try to find out KL by R. In my case, I have taken the reduction factor as 0.9 and L is 15 meters. So many millimeters, and R we computed as 263.86, which is coming to be 51.16. Now, since KL by R is less than Cc, I can use this equation. Okay, this equation is only valid for this condition. So, I have checked it, it is okay. I am going to use this equation. Okay, let me use that equation and substitute. So, now I can find Fa as 1 minus 51.16 square, that is KL by R square divided by, okay, there is a Fy here, I think we have written it there, there is Fy here, okay, please understand, there is an Fy here. Fy is here divided by 2 times of Cc square, it is 106.92 into, of course, 345, that is Fy divided by 5 by 3 plus 3 KL by R we know, which is 51.16, and we also know CC, so 8 into 106.92 minus 51.16 cube divided by 8 times of 106.92 cube. Okay. Substitute this and try to see, I get this value as 166.72 megapascal. Okay. Now, the elastic buckling stress is to be calculated, because we must know whether the system is going to be inelastic or elastic. So, why do we know this? Let us understand. For members whose d by t is less than 60, the member will undergo local buckling. The failure will be preceded by local buckling, before it fails in column buckling mode. That is very important. Hence, Fy in determining Cc and Fa should be replaced, because I am focusing on local buckling. It should be replaced either by elastic buckling stress or by inelastic buckling stress, whichever is lesser. So, let us compute that now. So, the elastic buckling stress which is Fxe is given as 2C E T by D, where C is generally 0.6, but literature advocates this to be 0.3, because to account for local imperfections. And Fxc, inelastic buckling stress, is given as Fy times of 1.64 minus 0.23 times of d by t to the power 0.25, and of course, this is to be limited within Fxc. Okay. And Fxc is equal to Fy for d by t greater than 60, less than equal to 60. So, let us see for the present case what happens. So, for the present case, we find Fxc. Let us find first Cc. Cc is 106.92. We computed that, right? We compute Cc. Oh, we are going to compute that, right? Let us do this. Cc is going to be square root of 2 pi square E by Fy, which is square root of 2 pi square 2 10 power 5 by 345, which says 106.9. Then let us know the K by L by R value, which is 51.16. We already computed this. Since KL by R is less than Cc, Okay, we have computed FA as 166.72 megapascal. We did that, right? See here, FA we computed. Okay, I am writing it here. We computed this. Now let us compute the elastic buckling stress. Fxc is 2Ce T by D, which I say 2, I am using 0.3 and E is 2 10 power 5. Thickness we already know 15.88 and D we already know is 762. So, this comes to 2500.78 megapascal, accounting for geometric imperfections. For D by T less than 60, Fxc is Fy, which is 345 megapascal. Okay. So, now let us prepare the allowable bending stress. The allowable bending stress Fb is given as 0.75 Fy or other equations depending upon the case. So, let us check the case now. For the present case, let us say 10,340 by Fy less than 762 by T less than 2680 by 345. That is the case. Okay. So, for this specific case, Fb is given by this equation 0.84 minus 1.74 times of Fy d by E t times of Fy. Okay. Let us compute this. Please substitute this, which comes to be Fb is equal to 0.84 minus 1.74 times of 345 into 762 by 2 10 power 5 into 15.88 of 345, which comes to 240.1 megapascal. Now, let us apply the unit check. The unit check 1 says Fa by Fa plus Cm times of Fbx square plus Fba square divided by 1 minus Fa by Fe dash times of Fb should be less than or equal to 1.0, right. Let us first compute Cm is given as 1 minus 0.4 times of Fa by Fe dash or 0.85, whichever is less. So, let us say for Fa by Fa less than 0.15, we can apply a single check. Okay, we already saw the equation. Let us see what is the present case. the applied axial stress FA is P by A. So, P we know 1200 10 power 3 newtons, A we know 3.72 10 power 4, which comes to 32.26 megapascal. The applied bending stress let us work out in plane, which is FBY, which is My by Z, which is 800 10 power 6 by 6.8 10 power 6, which is 117.64 megapascal. Out of plane stress FBX is Mx by Z, which is 600 by 6.8 10 power 6, which is 88.24 megapascal. So, now let us compute Fe prime, which is given as pi square E by KL by R square into 12 by 23. Let us compute that. Pi square into 2 10 power 5 by 51.16 square of 12 by 23, which is 393.1 megapascal. So, now in the present case, Fa by Fa, which is 32.26 by 166.72 is 0.19, it exceeds 0.15. So, I must use two conditions, and therefore, Cm now becomes 1 minus 0.4 times of 32.26 by 393.1, which is here, okay, which comes to 0.96, but it cannot be more than 0.85. So, let us do UC1. The unitary check 1 says Fa by Fa plus Cm times of Fbx square plus Fby square divided by 1 minus Fa by Fe dash of Fb should be less than or equal to 1.0. Let us substitute this, which becomes 32.26 by 166.72 plus Cm is 0.85, there is a limiting factor, square root of 117.64 square plus 88.24 square. We computed these values here, please see. Okay, I am using those values here. Square divided by 1 minus 32.26 by 166 point, not this, Fe prime, which is 393.1, 393.1 times Fb, which is 240.11. We computed that, right? See here, Fb we computed. Bending stress. Okay. So, the value I am using that here. So, now I compute this value and found to be 0.76 less than 1. So, I can say the brace is safe. Let us do unitary check 2, UC2. The second condition says FA by 0.76 FY plus square root of FBX square FBY square divided by FB should be less than or equal to 1.0. Let us substitute that. So, 32.26 by 0.6 of 345 plus square root of 117.64 plus 88.24 divided by 240.11, and that value comes to be 0.76 less than 1. So, the brace is safe in both conditions. So, friends, let us come to the summary of this lecture. In summary, we say that in this lecture we understood why a brace will be under biaxial bending, and under axial tension combined together, how do you perform the unity check. We also illustrated a design example of a brace subjected to both mx and my in plane out of plane bending for a given d by t for a given KL by R ratio. We use the equations and check unity check 1, unity check 2, and we found that say brace is safe. If by chance the brace becomes unsafe, you have got to change the cross sectional dimensions of the brace, thickness and diameter ratios, or select an upper grade of steel. In this case, we have taken a steel Fy of 345, we can go for a better grade of steel and so on. Friends, probably I think you will be able to revise this design example once again for other substituted values. Try to use the codal example and try to use these equations and check yourself. One can also write a simple MATLAB program for finding this unitary check faster, and you can make your understanding more reinforced manner. Thank you very much. Namaste.